Thank you very much. First of all, well, thanks to the organizers. I really love being here. I've learned a lot this week, and I hope I have a little piece to add for some of you on what new we heard during that week. I should mention what I'm talking about is joint work with Christine Bibby and Graham Dunham. And so what do I want to talk about? I want to talk about rational models of hyperplane complements. And as Alex rightfully pointed out earlier this week, well, they're as formal as it can get. Why would you think about rational models? I want to take the freedom to think a little bit about it and discuss some long-standing, long-known Leray model for the arrangement complement of because it reconciles in a nice way the, say, broken circuit or Orlik-Solomon combinatorics that we all know and love, and the continued Borghese combinatorics of building sets and nested sets. It's just nice to see that in one picture, I suppose. And also from there, of course, I want to go a step further. This is all geometry, and the Leray model works because we have the Leray spectral sequence and we know it very well and we understand it very well. What if we step out into the world of non-realizable matroids? What is left of this story? And the nice thing is I can present you a graded differential graded algebra, in a way a rational model for the Orlik-Solomon algebra of a matroid with no reference to underlying geometry whatsoever. And that's the challenge, of course, to take enough inspiration from the geometric case and to do bare hand with shear combinatorics, reproduce what has been done in the geometric setting, knowing that this world of non-realizable matroids out there is huge and not as well understood as we should understand. So let me introduce the layers briefly, which means also introduce the notation. So for me, A is an arrangement of n hyperplanes in some complex projective space, I mentioned before. And I call script L its intersection matrix. I call M a complement. And I denote is OS of A, the Orlik-Solomon algebra. So the cohomology algebra of the complement, for the sake of this talk, with rational coefficients has been up on the board. I don't need to write this down here. Let me jump to the continued Borghese type combinatorics or combinatorics underlying their models, because it's less known and you probably are less familiar with that. What I'll need is certain subsets of this intersection lattice. We call them building sets. With a bit of tedious combinatorial definition, let me give the essence of it. Or let's say, first a definition by example. There's always a maximal building set, G max, which is the full lattice. So whenever I say building set, feel free to think about the lattice and that's it. But there is also a minimal one. And this is the set of irreducibles in L. So elements in L such that the lower interval doesn't allow a product decomposition. The whole world of building sets lives in between. And what the essence is well, so whenever in your lattice you have an element and you look for all the building set elements that are maximal below that. So look at G, the maximum elements of G less or equal to X. And you build, then they come with lower intervals. And what you find is that the lower interval under X is the product of all this, let's say G1 to GT. So what I want to say is that building set elements are prospective factors of product decompositions in your lattice. That's what you could possibly think of it. A nice example to keep in mind in the famous partition lattice is, well, take the irreducibles. In the partition lattice, the irreducibles are the partitions with just one non-trivial block. This is a non-trivial example, which gives you quite a bit of insight if you keep this in your mind if we go along. With the choice of a building set comes a complex, a simplicial complex, the complex of nested sets. I tell you, so as a subset of such a building set is nested, and that's one definition I want to give because I want to work with it. If for any subset in S, G1, GT, and S, Y is incomparable. The join over these GI E equal 1 to T is not an element of the building set. Okay. So if we look at the examples I just mentioned, this forms a simplicial complex. So NG is a nested set complex. And if we look at this maximal building set here, so N of L, nothing else but the order complex, because all the chains are going to be listed. But in general, of course, it's going to be more than the chains, but for this maximal example is just the chains. For a general building set, the nested set complex is going to be a subdivision. It's going to be a subdivision of the order complex. That's right, and it's even going to be homeomorphic. So in general, so for some G prime less, no. Yeah, that's a way to write it. So G prime contained in G max, contained in L, will have that the nested set complex, and G is homeomorphic to L, which is the order complex of L. So topologically, it's not much in there, but in terms of subdivision, of course, you have a whole world of a whole hierarchy of subdivisions there. Okay, where are we going to use this? This we are going to use in a kind of as a combinatorial essence of the differentiated purchasing model construction. So, for the complement of A. Well, it's about looking at the inclusion of MA into a product of projective spaces, kind of copying over and recording relative positions of points in the complement with respect to well, arrangement strata indexed by the building set. So projectivization of CR G or G in G. And we take the discontinuous quadratic compactification, YA with a choice of the building set is the closure of the image of this.
In that space, in the projected space.
Yes. So, what are the facts we need to keep in mind, which makes kind of the combinatorial game going? Well, first of all, by construction, this is a smooth projective variety. It contains the original arrangement complement, and the complement in turn is a divisor with normal crossings. It's the union of irreducible components, DG, indexed over the elements of the building set, means a particularly chosen subset of the lattice. So this is a divisor with normal crossings. You might guess from what I was talking about, the nested set complex is what tells you when do these divisor components intersect. So the intersection of DG, G in full subset is non-empty if and only if S is a nested set. Now let me define an algebra, which is our analog of the Orlik-Solomon algebra, kind of for the computation. DPAG, the Di-Concini-Procesi algebra. It's the quotient of a polynomial algebra, dxg, gg, generated given by building set elements, modulo the following relations. First of all, we're thinking cohomology already, so we want products over generators to vanish whenever they are indexed by a set which is not nested. So let's say the product over x, g, g and s is going to give us a relation that we use the notation x lower s, find s, whenever s is not nested. So any non-nested set gives you a relation, and we need to add a linear relation for every hyperplane xg, sum of all xg, for everything which lives over a particular hyperplane H, for any hyperplane H in A. We'll have guessed by now, this is the cohomology algebra of the Di-Concini compactification. So GP of AG, in fact, is the cohomology of the model. So credit for this. So this is all in the original paper by Di-Concini selected as a series of papers from 95. This is a slight simplification, but that's all you can essentially find in there. I want to add one particular piece of information, which is not that well known, I guess. There's a nice monomial basis due to Sergei Uzvinsky. So Di-Concini was 95. I think this paper appeared in Inventiones 97. And the basis looks as follows. So it's monomials x a exponent 1a over nested sets. So S is a nested set complex, and the exponent should be smaller than the rank difference between A and A prime. A is the particular element in S we are looking at, and A prime is the join of whatever lives below in S. It's the join of S less than A. So in our lattice, if we have A here, there are some elements of S which live below. They have a join, they join up in A prime. And yes, there is a difference here because join of a subset of a nested set is not going to live in the set. Whereas this is a building set element, so we have a difference here. And this allows for interesting experiments. Let me turn to the rational model. Second part, our inspiration for the matroid case, a rational model for the complement of A. I'll write down a bigraded algebra, BAG, and that's going to be inspire me for the combinatorial work. It has generators of type E and type X, both indexed by building set elements. Modulo, and here come relations, or I should say the degree of EG is 0, 1. They're going to be skew commutative. And the degree of XG, this is commutative generators, is 2, 0. Okay. Relations. Relations are of the form ES times XT, where S and T are subsets of G. I use the same notation as over there. And I require, well, first of all, want them to be disjoint. And I want their union not to be in the nested set complex of G. And what more? I want to model the relation we see over there. I want to put the sum of all XG, where G is larger equals some H a hyperplane in A. This I want to put to 0. Okay, the differential is so easy to guess. D of VG, XG, and D of XG is 0.
Skew commuting?
Sorry?
Question.
I'm sorry.
Did you say that the E variables are commuting or skew commuting?
The E variables are skew commuting among each other, and so I mean as by degree is telling you in a way. So the picture to have in mind, and already the explanation why this is going to work. Well, what does it look like? We have a below where only every second column is interesting. And so on. Here live the EGs. Here live the XGs. And actually, so if you look at what happens in this first column here, we see that by the relations that only depend on G, we see this is the exterior phase ring of the nested set complex, which lives in this first column. And what lives in the first row, by looking at relations again, is the continuous algebra. So what lives here is actually the cohomology of the decontinuous compactification.
Just to make sure, so the first column comes from T equal the empty set, and X sub empty set is 1.
Right,
That's the
it comes
convention.
from disregarding the X, right? It's generated by the E's.
Right, but
Huh?
the relations just involve ES times XT. So I was saying X sub empty set is 1.
T is empty, S is non-nested. Yeah. Okay. So you recognize that this is, of course, the E2 tableau of the Leray spectral sequence, which comes from the inclusion. And by all work of, long known, Loyenga, Totaro, and others, we know this this converges, the differential vanishes after this term, and what the result is that the next tableau is just going to have the Orlik-Solomon algebra in this first column. So I said I want to lift this to matrix. And what the main idea is to look at the De Concini-Procesi computation in a slightly different way. So let's take the definition I had up here on the board. Let's say, well, let's remind ourselves it's the result of a sequence of blowups of substrata indexed by building set elements in a suitable order. That's all. So if we understand, we now look at the lattice, and if we understand what a combinatorial blowup, what a combinatorial operation on this lattice should be that corresponds to blowup, then this is our stepping stone for a combinatorial construction. So let's say third part, remember YAG is the result of successive blowups
You know, you have to make the conversion.
going up further indexed by building set elements. So let's say we start with complex projective space stratified by derangement. We have blowups. And we find the compactification stratified by the divisor components. Combinatorially, the combinatorial analog of this is, well, we start with the intersection lattice. And obviously we end up with something which, well, we end up with a face posted of the nested set complex. That's what we want to see here. That's the way these things intersect. Well, the face posted of energy, and the question is, what is in here? Well, what is the construction that makes this work? And the construction makes this work is a blow up in the poset sense. Say I have an element in a lattice, or say my lattice for this matter, and or actually I just need a reasonable joint type operation. You can make this very general. What is the blow up of the lattice in X? Well, it is take everything which doesn't know about X. So take all the Y's that are not larger, not larger equal X. So as a mathematically, lattice, here's my element X, and everything on top I remove, throw it away. And now I add something. I add a copy of this in a way. So Y prime for which Y is not larger equal X. But I want that Y join X exists now. So I take things which live, well, somewhere here, Y, which still have a join with X in the original L. Now, as I take away X, it won't have anymore. So I artificially add it. So I take a copy of this thing over here. So my Y prime is going to live over here, and I put in order relations. So for the minimal element, I'll have some kind of a 0 prime here by construction. And I'll think about this 0 prime as the exceptional divisor, which as what happens to X when I blow it up. So it's kind of my X twiddle or something. Right. This is a construction I studied with this comes in handy here. So actually, if you iterate, if you take the blow up along the chosen subset, along this chosen element of the building set in a suitable order. What you get working on your intersection lattice is the face poset of the nested set. So this is the combinatorics, which makes the algebra construction work. Clean board. I want to define an analog of this bi-graded algebra. Just my input is not going to be A, my input is going to be a matroid, a simple matroid. And I want to define a sequence of such, which kind of runs along this sequence of blowups that I have described here. So, say I start with simple matroid. On elements. And now I drop the script to distinguish. L is my lattice of flats. Yeah.
Say it again, was the process structure with respect to the y primes?
Yeah. So the y primes are a copy of this part which I just threw away. I put it next to it, but kind of one rank higher if you think about, I mean, if they're one rank function, then it would work out this way.
The ones which are below y prime.
It is what was living in here below the join of x and y. This is a copy of x and y. I choose a building set in L. I can do this without reference to geometry. That's purely combinatorial method that is useful in the lattice of flats. And well, then I have a sequence of, let's be careful, let's say posets. Let's not go into too much technicality here. It starts with L0, which is L. It goes all the way, and there's an LJ here, which is the blow up of LJ minus 1 in GJ. And there is, as we learned, there is the last one here, this LP, which is the face lattice of nested set. I'll need, so I have a whole sequence of posets now, which govern kind of the way things intersect or are stratified. I need a complex which governs the way things intersect, and that's going to be an analog of the nested set complex. Let's define it here. So the J's one is going to be atoms or subsets of atoms in this poset in LJ, such that the join of them exists in J minus 1. Now J, so it's something, it's in a way an atomic complex associated with this poset. Well, if you do this on this last one there, you get the nested set complex, right? So N of T is the nested set complex of G. Oh, I'm ready to define the algebras. indexed along my building set elements. So depending on depending on the choice of building set, and they run from 0 to t. By graded, we can have a look over there. It's pretty similar, but a little more complicated. EG, XG. These are actually in LJ. Yes. Modulo relations. So observe as I build up, as I go along B0, B1, and so on, generators get more and more. I start with the atoms of L, then I add one building set element at a time. I might end up with my full lattice. I might end up with something which I've chosen before, namely a suitable subset of this lattice. So it's adding two generators at a time combinatorially by making these building set elements which used to live in a higher codimension by making them atoms, by bumping them down. Yeah, the degrees I take from over there. So my EGs live in 0, 1. They generate a leftmost column if you want. So the XGs live in 0, 2. They generate the bottom row. So what are the relations? This is the interesting part. So this ideal generated 3 times types of relation generated by. So first one is pretty much the one over there, ES XT. The union not in the appropriate nested set complex, in the one which runs along my sequence of blowups. That's why I have the index here. Second, or some kind of an Orlik-Solomon relation. It's a delta ES, and I refer to the usual Orlik-Solomon notation, where S is nested with respect to the poset I start with, so it's nested in MJ, and I wanted to be dependent, so the rank of the join of S is less the order of S. Okay, and the third looks very similar like the one over there, just a little more complicated because my number of atoms is varying all the time, so it has to vary from step to step. It's again a sum over generated J. J are the atoms, in LJ, and the G used to be larger than I in the original L. Just have a look. So degrees, differentials are the same as before. Differential, so EG gets sent to XG, and XG gets sent to Z.
Explain that with something over G bigger than I, bigger in L of I.
Yeah. So it's,
What do you mean by that?
I take, so at the particular blow up step I'm at, I have atoms.
Yes.
I take all the atoms, I sum them up. But if I just take those, which in the original lattice, when there were elements somewhere up there,
Yeah.
live on top of the ice hyperplane.
Oh, I see. Okay, that's what
Yeah, the relations too, which are like these Orlik-Solomon type of relations, they're missing in there. So
They are missing there, that's right.
so you put them now only here.
I put them in
Okay,
because
yeah,
we want, they are, yeah. So,
Delta.
right. Well, it's, so you'll see when, let's see, observations. If we take, so what is B0? If I look at B0, the whole thing lives on my original lattice. the generators correspond to the atoms. And if we look at this relation, it means that we can already discard of the X generators. Just lives on E. And when we look at what it does when it lives on E, here we see the Orlik-Solomon relation that we expect. And this, so the X terms don't matter, the E terms give the projective Orlik-Solomon relations. It's those which don't, it's the non-spanning subsets. So B0, in fact, is the Orlik-Solomon algebra of the matrix. And on the other end of the spectrum, BT is kind of a variation of this one because well, this doesn't refer to the geometry either, right? It's if I go and write this down in pure matrix terms, I'll write the same thing. So I'll say this is BMG, like up there on the left.
So
Why?
the NT is empty then?
No, that's wait. So the S here is no, it's the face poset of the nested set complex, and we don't have any dependent sets in there.
Okay.
So this discards this type of generators.
Okay.
Okay, so I briefly tell you, because I'm almost out of time, how these things tie together. Because so just with the overview we have. Graded commutative differential graded algebras. We're going to define maps. Y0, connecting them. On T minus 1. On the left end of the spectrum, we see the Orlik-Solomon algebra of M. On the right-hand side, we see well, what we call BMG, but observe. So what I want to say is just the bottom row is, well, yeah, it's a de Conchita-Cortese algebra of what? Well, let's say it's the towering of the matroid. If you look at the defining relations, exactly what it is. So we get a sequence of differential graded algebras and maps, which are actually so the crucial fact then, of course, crucial fact, those phi quasi-isomorphisms. Well, this means all the algebras we construct here, they in a way they interpolate between the Orlik-Solomon algebra of the matroid and the towering of the matroid. A few keywords on how to process this, of course, a tedious thing. The key ingredient is actually a Gröbner basis for the ideals that we carry along. This Gröbner basis for the ideals give us a monomial basis for the differential graded algebras, which specialize as they should. They specialize to the broken circuit, to the non-broken circuit basis on the left hand here, and they specialize to Józwiński's basis that I presented you earlier for the analog of the de Conchita-Cortese algebra, which is the towering of the matroid. And that's pretty much the ingredients we need. So the Gröbner basis, the monomial basis for the algebras, and actually what happens also is on every level, kind of a brief point of composition of this BI into a part which corresponds to an Orlik-Solomon algebra of the localization and a discontinuous Procesian algebra of the stratum, the local stratum. So something which we know from the arrangement world very well. Purely in this matroid type of setting. This is the ingredients we need to make this combinatorial analog. I'm over time, so thank you very much.